infinite limits and limits at infinity. So infinite limits and vertical asymptotes. A limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. If f of x approaches positive or negative infinity as x approaches c from the right or the left, then x equals c is a vertical asymptote of the graph of f of x. So here's a quick example. Here we have the graph of f of x, and here at x equals 0, so the graph sort of goes up to infinity from the left, and from the right it goes down to negative infinity. And here we call x equals 0 a vertical asymptote. So here the problem, the function 1 over x minus 2. If you just plug in 2 into f of x, because you're going to find this limit as x approaches 2, if you just plug in 2, you're going to get 1 over 2 minus 2, which is 1 over 0. So this would end up being, this limit does not exist. But we're going to have a bit to show some further proof of that. You just say it does not exist. Remember that the definition of a limit is it's approaching this x value from the right and from the left. So what we're going to do is we're going to evaluate the limit as x approaching 2 from the left and as x approaching 2 from the right. Now how do we do that? We just have this one function right here. Well, as we're approaching 2 from the left, the values go from like 1, 1.5, 1.9, 1.99, 1.999. It's going to approach 2 from the left like that. So you can plug in a value that's really, really close to 2. Let's say 1 over 1.999 minus 2, right? Evaluate that 1.999 minus 2. Since 1.999 is less than 2, it's going to be like a really small negative value. I think in this case it's 0.001. So this is negative. I think this is, yeah, this is going to be negative 1,000. Keep in mind that this is negative, and it's going to be 1 over a really small number, like 0.001, which is going to give you a really big number, like 1,000 here. And if you use 1.9999, then it would be negative 0.0001, which turns to be negative 10,000, and keep going. And you can see the numbers just keep getting bigger and bigger and bigger, but it's negative. So this limit here is x approaching 2 from the left. It's approaching negative infinity. It's the same thing, but approaching 2 from the right. So you have a value that's really, really close to 2. Since approaching from the right, it's going to be over 2. It's going to be really, really close to 2 though. So let's say 2.0001 minus 2. That comes out to be 1 over 0.0001. About 10,000. You see where I'm going with this. Now, this number on the bottom is positive now, because it's coming from the right. This number, 2.0001, is greater than 2. This is going to come out to a positive number. When you're dividing 1 over a really small number, you're going to get another really big number. But this time it's going to be positive instead of negative. See, the limit as x approaching 2 from the right is positive infinity. What the graph looks like, it looks something like this. So you'd have this here is x equals 2. And from the left, it's going down, it's approaching negative infinity. From the right, it's going up, it's approaching positive infinity. Now, since these two limits are not the same, so you have limit as x approaches 2 from the left of f of x is not equal to limit as x approaches 2 from the right of f of x. This limit cannot exist. It does not exist. Because these two limits are not equal. So the limit as a whole, just limit as x approaches 2, it just doesn't exist. We have f of x equals x plus 1 over x squared minus 1. Oh, first, here's VA stands for vertical asymptote. Since we evaluated this limit, it does not exist as it approaches negative infinity from the left and positive infinity from the right. X equals 2 can be considered a vertical asymptote. You see right here, it's a vertical asymptote. The function approaches x equals 2, but it never actually touches it. It just goes straight down to negative infinity, straight to positive infinity. Vertical asymptote right here. Okay, now x plus 1 over x squared minus 1. Here's the limit as x approaches negative 1 of f of x. And what we can do here, see if you plug in negative 1 into here, you're going to get 0 over 0. So we're going to need to, actually no, we're not going to get, you're going to get 0 over negative 2. Let's do this, this one first. Limit as x approaches, okay, limit as x approaches negative 1. The first step we're going to do is we're going to factor this out into x plus 1 and x minus 1. You'll instantly know if you see a difference of two squares, x squared, and this is 1 squared. And we factor into x plus 1, x minus 1. It's a very useful thing to memorize for factoring. Anyway, we have x plus 1 over x plus 1 times x minus 1. So this is going to cancel out. What you'll get is limit as x approaches negative 1 of 1 over x minus 1. Now I can just plug in negative 1 for x here. Get 1 over negative 1 minus 1. There's going to be 1 over negative 2, which is going to be negative 1/2. So limit as x approaches negative 1 of f of x is negative 1/2. Now let's keep going here. We already factored it out here, so we can just bring it down. Limit as x approaches 1 of f of x. The limit as x approaches 1 of 1 over x minus 1. So we factored it out right here. Just bring it down. See, now if you plug in 1, you're going to get 1 over 0, which is some kind of infinite value. So you're going to, now you're going to have to write values for the left and values from the right of 1. Now it's the same situation as last time. You get limit as x approaches 1 from the left. So you have like 1 over some number that's really close to 1, but from the left, so like 0.999 minus 1. And what you get is 1 over negative like 0.001. And this number is just going to keep getting like smaller and smaller as you keep approaching infinity. So the result is going to keep getting like bigger and bigger. Right now it's negative 1,000, it can be negative 10,000, negative 100,000. It's going to keep going until it reaches negative infinity. Same thing with here. We're approaching 1 from the right. Like 1.0001 minus 1. Now you have like a positive number with a denominator, which means this limit here is approaching positive infinity. And since the limits from the left and the limits from the right are not equal, now we can write that this limit f of x as x approaches 1 is dne, does not exist. And so because of that, we can now write that x equals 1 is a vertical asymptote of f of x. Now this number here, -1, this isn't a vertical asymptote of f of x. This is merely a hole in the function. So you're going to have this function looks something like this. Which is, it looks like 1 over x minus 1. Right, but it's actually x plus 1 over x squared minus 1. Because here, at x equals 1, you'll have your vertical asymptote. But at x equals -1, you're going to have a hole. As we'll learn later, it's called a discontinuity. But you have a hole here at -1, -1/2. And so x equals 1 is the only vertical asymptote. This value x equals -1, this isn't a vertical asymptote, it's just a hole in the function. Here you have another one. This one's slightly more complicated, but first step is to factor it out. And notice for the numerator, we have x on in both terms. So we can factor out an x, and we can leave out x divided by x squared divided by x is x, and -3x divided by x is just -3. So factor out an x. It's best to factor out as much as you can when you're factoring problems like these. So x squared minus 4x plus 3. You factor that out. You can have, so what two numbers multiplied at 3 and add to -4, that'd be -3, -1. So you have x minus 3 and x minus 1. You'll see x minus 3 on the top and the bottom, so these can cancel out. You're left with the limit as x approaches 3 of x over x minus 1. Now you can plug in 3 for x. You get 3 over 3 minus 1, 3/2. So this is x equals 3 is just another hole in the function we have here. Now let's evaluate the limit of f of x as x approaches 1. We already factored out here, so we're just going to bring this down. Limit as x approaches 1 of x over x minus 1. Notice if you plug in 1, you're going to get 1 over 0. So that's another infinite limit. What we have to do again is evaluate the limit from the left and from the right. And eventually you'll learn just how to do this without needing to write all this out. But x approaches 1 from the left, so I'm not going to write it out this time. It's going to be like from the left, it's going to be like 0.999, right? And 0.999 minus 1 is going to be like -0.001. So you're going to have a small negative number in the denominator, and that's how you know it's approaching negative infinity. Same thing for the plus. For the plus, you have 1.001 minus 1. You'll have a positive 0.001 in the denominator. So this limit's approaching positive infinity. And since the two limits aren't equal, again, then this limit does not exist. And so we can write that the vertical asymptote of this function is at x equals 1. Now I have f of x equals secant x. And the first step to do here is to consider secant x. Remember that secant x is the same thing as 1 over cosine x. Now for this problem, it may be helpful to just draw out the unit circle. So you have pi over 2 here, and 3 pi over 2 here. Remember that cosine is the x value on the unit circle. So that means if you plug in pi over 2, the cosine of pi over 2, and see it's 0, because this point is 0, 0 here. So the cosine of pi over 2 is 0. That means you'd get 1 over 0. So what that means is if you evaluate the limit from the left and from the right. Now you have to think about this one a little bit differently, because it's a unit circle limit, or like it's a trig limit instead of just the normal rational limits. So if you're approaching pi over 2 from the left, and you'd have a number really close to here. This is 0 to pi over 2. It's going to be like this. You have a value slightly greater than 0. But it's approaching 0, but it's still greater. What that means is that you have 1 over cosine x, so cosine x is slightly bigger than 0. Let's say 0.0001, right? That means you'd have a really big positive number. As we discussed before, that means the limit as x approaching pi over 2 from the left is positive infinity. Now let's do the same thing from the right. From the right, you have a cosine value that's slightly less than 0. That means you'd have a negative, a really tiny negative cosine value, which would lead to a really big negative number, because this limit approaches negative infinity. And of course, since these two limits aren't the same, that means this limit does not exist. Now I can do the same thing for 3 pi over 2. From the left and from the right. So for 3 pi over 2, if you're approaching it from the left, you'll get a value that's slightly less than 0. Since this value is negative, that means you'll get negative infinity as you're approaching from the left. From the right, you'll get a value that's slightly greater than 0, as you're approaching from the right. So you'd get positive infinity. Still, these aren't equal, so that means this limit also does not exist. But pay attention to the fact that it's not always going to be negative infinity from the left and positive infinity from the right. Sometimes it's going to be positive infinity from the left and negative infinity from the right. You just have to pay attention to like the sign of the equation, and if it's like a trig problem. And this is a helpful visual for when you're solving those types of problems. Now to write the vertical asymptote for this one, this is going to be a little bit different. So pi over 2 and 3 pi over 2, they're both vertical asymptotes, right? Because these limits don't exist. But the thing about trig and like degrees and radians is that they can sort of go on forever. So this pi over 2, it's also 5 pi over 2. And this 3 pi over 2 can also be the same as 7 pi over 2. It can go on. This can be 9 pi over 2. This can be 11 pi over 2. And so, if you're writing the vertical asymptote for this, you write pi over 2 plus 2 pi k, and also 3 pi over 2 plus 2 pi k. And k is just any number. You can add 2 pi and you'll still get the same thing, and that's why it doesn't really matter what k is. K is just some random integer. The reason this is important to add this k is because the function keeps going forever. It has an infinite amount of vertical asymptotes. Secant x looks something like this. So you have a vertical asymptote here, and here, and here, and here, and it'll keep going on like this forever. But notice that pi over 2 and 3 pi over 2 are only 1 pi apart. Right? Because 1 half and 3 halves, there's 3 halves minus 1 half is just 1. These are pi apart. And you can just get this is pi, this is pi. So instead of writing all this, just write pi over 2 plus pi k. So you'll have a vertical asymptote at pi over 2, and if you add another pi, you're going to get 3 pi over 2, add another pi, you're going to get 5 pi over 2, add another pi, you're going to get 7 pi over 2. These are all vertical asymptotes of secant x. This is a definition of a horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of fx equals L, or the limit as x approaches positive infinity of fx equals L. Now here's some tricks to find those limits at infinity. If the degree of the numerator is less than the degree of the denominator, then the limit is 0. So you're probably going to have a function that's on this line here. It's not exactly on the line, but 0 is this this horizontal asymptote of the function. So let's say if you have x squared over x to the 4th, because 4 here is bigger than 2, and it's on the bottom, then the horizontal asymptote is 0. If the degree of the numerator is equal to the degree of the denominator, the limit is the ratio of the leading coefficients. What that means, if you have the same degree on both the numerator and the denominator, then you look at these leading coefficients in front of it, and you just take the ratio of it. So you have 3 and 6 here, then the horizontal asymptote would be 3 over 6, or 1/2. Now, if the degree of the numerator is greater than the degree of the denominator, the limit fails to exist. So since here 5 is greater than 3, and it's on the top, the limit is dne. And what the graph is usually going to look like is it might look something like this. There's no horizontal asymptote exactly, because this function keeps going on forever towards negative infinity and towards positive infinity in both directions. Let's practice. Here we're gonna use the tricks I mentioned earlier. There's 2 ways to evaluate horizontal asymptotes. Here's the first one. So the greatest degree is here on the top. You have 2x. This is 2x to the first power. And the bottom, your greatest power is 2 over x squared. Now that means the horizontal asymptote is 0. You can provide a little bit of an explanation. So let's say you have infinity. Let's say I actually plugged in infinity into this. Let's actually do that. 2 infinity plus 5. This isn't mathematically correct, but it's just good for demonstration. Over 3 infinity minus infinity squared. We can talk about this 2 infinity plus 5 real quick. So let's say you have $1 billion or $1 trillion or $1 trillion, right? And someone gives you $5. That $5 means absolutely nothing to you because you have so much like money to begin with. That $5, that's absolutely nothing. This is completely insignificant, right? So you would just have like 2 infinity to consider. Because I mean, if you add 5 to it, that's basically adding nothing. It doesn't really change it at all. That's how big this 2 infinity is. Now 3 infinity minus infinity squared. You actually want to ignore this 3 infinity because you only want to take the biggest degrees, which is in this case is 2. And the reason, let me illustrate this again. So let's say you have infinity. Instead of infinity, you have a really large number, like 1 billion, right? And let's say I have 3 times a billion. So let's say I have $3 billion, right? And you have this infinity squared right here. So you have $1 billion squared dollars, which is like a billion, right? My billion is going to mean absolutely nothing when compared to your billions. You have 999 million more billions than I do. And so this 3 infinity here is just, it's insignificant. It doesn't really matter. So you can consider this as 2 infinity over negative infinity squared. And now you can have this analogy again, where like now I have 2 instead of 3. So now I have two like $1 billion, right? And you have $1 billion. This $2 billion means nothing when compared to this $1 billion. And so you have something like a really small number divided by this infinitely big number here. And when you do that, it's essentially 0. That's like cutting a cake into an infinite amount of pieces. Or if you want, it's essentially 0 because you're dividing such a small number over such a huge number that it just becomes like so small that it basically ceases to exist. If I cut the cake into like an infinite amount of pieces, each piece is basically nothing, right? And so if you go to a party and you have to cut this tiny little cake for like 1 million people equally, right? You cut this cake for 1 million people and you get a piece. You probably won't even be able to see the piece of cake you get because it can be just that small. It's basically 0. It's basically nothing to you. And that's why if you have a bigger degree on the bottom than on the top, your horizontal asymptote is going to be 0. Here's another method to use. If you don't like using little tricks, you can just try to plug in infinity. Now, of course, this isn't mathematically correct, but this is just for a demonstration, right? Again, this negative 5 infinity has absolutely no effect on this 3 infinity squared, it means basically nothing. Same thing with this 2. That also means basically nothing. In other words, you're only gonna take the biggest coefficients and you're gonna ignore everything else. So you have 3 infinity squared over negative 4 infinity squared. Now this infinity squared and this infinity squared here on the top and the bottom, they'll cancel out. So you're just left with negative 3/4. The same thing happens if you substitute negative infinity. Again, you can ignore these. They're basically insignificant. And negative infinity squared, because squared, any number squared is positive. So it's basically the same as 3 infinity squared over negative 4 infinity squared. And still these cancel out. You get negative 3/4 again. And your vertical asymptote, your horizontal asymptote, is y equals 3/4, negative 3/4. Here's another one. 6x squared plus x cubed over 2x squared minus 1. And you're going to take only the biggest coefficients matter. So again, this 6 infinity squared is nothing when compared to this infinity cube. This is infinity times infinity times infinity, and this is just infinity times 6. This means nothing, right? Same with this minus 1. This minus 1 means nothing when you're comparing it to like infinity, right? So now you're just considering infinity cubed over 2 infinity squared. If you want, you can like cancel out the infinity squared on both sides, so you just have infinity over 2. But now you're left with this infinite value, right? And the function, just graph it real quick so I can provide a visual representation. It'll look something like this. So you have and try to find the limit as x approaches infinity, right? There's no horizontal asymptote that just keeps stretching on and on and on into y equals infinity. This limit, this horizontal asymptote, it just does not exist because there is no horizontal asymptote in this for this function, because the biggest degree in the numerator is greater than the biggest degree in the denominator. Here's an interesting one. The square root of 4x squared minus x over 3x plus 5. And they might just be thinking, you can just square root 4x squared, right? And that's true, except you'll be getting the absolute value of 2x. And that's because if you plug in, let's say we have square root of 4x squared and 2x, right? These two are supposedly the same, right? Because square root of 4 is 2 and square root of x squared is x. But they're not, because if you plug in a negative value, let's say negative 1, and here you get negative 1 squared times 4, which is 4, and then the square root of 4 is 2. But if you plug in negative 1 here, you get negative 1 times 2, which is negative 2. So what you need to do, if you're taking the square root of a squared, then you need to put it in absolute value. And so that doesn't have much of an effect in this problem. You can just consider it as square root of x squared. That's just x to the 1, right? But keep in mind that this 4 is also being squared. So the first step, we're going to get rid of these non-leading coefficients. We're only going to consider the leading coefficients, right? So you're going to have absolute value of 2x over 3x, right? Because this is square root of 4x squared. X is going to cancel out on both sides. So you get 2/3 as the horizontal asymptote here. However, if you plug in, so that's if you just plug in infinity, right? If you plug in, let me just write it again. Plug in infinity into this, you're going to get 2 infinity over 3 infinity. The infinity just cancel out, right? That's really simple. But if you plug in negative infinity to here, since this is the absolute value of 2x, so you have absolute value of negative 2 infinity over negative 3 infinity. And basically what absolute value does is it makes all numbers positive. So you have negative 2, you have 2 infinity over negative 3 infinity. So now you have negative 2/3. So this function here has 2 horizontal asymptotes. One at 2/3 when it's going to the right, and one at negative 2/3 when it's going to the left. This is the last one. This is interesting. This is 5 to the power of x minus 3 over 2 plus 5 to the power of x. There's no real trick to help with this one, but you'll have to sort of plug in infinity and see what you get. That's the best way to solve these. So you have 5 to the power of infinity minus 3 over 2 plus 5 to the power of infinity. Now think about 5 to the power of infinity. That's just it's just an absolutely huge number, right? It's infinite, really. And so this minus 3 isn't going to mean anything. Adding 2 also isn't going to mean anything. So we're just left with 5 to the infinity over 5 to the infinity. It'll just cancel out to be 1. So you have one of the horizontal asymptotes at y equals 1. And do the same thing with negative infinity. But pay attention here because this is going to get a little bit weird. You're going to have 5 to the power of negative infinity minus 3 over 2 plus 5 to the power of negative infinity. Now what does 5 to the power of negative infinity mean? Well, if you have any number to a negative power, it just equals 1 over that number to that power. So you can rewrite this as 1 over 5 to the infinity minus 3 over 2 plus 1 over 5 to the infinity. Now 1 over 5 to the infinity. 5 to the infinity is just an absolutely huge number. And again, this is 1, this really small number, over 5 to the infinity. this really big number. Again, if I cut a cake into an infinite amount of pieces, and I give one piece to you, you're going to say it's basically nothing, right? Because I cut the cake into so many pieces, right? Because I gotta feed an infinite amount of people, right? No, this is your piece. Like this is your piece. You know, it's nothing. And so this number here, 1 over 5 to the infinity, it's basically the same thing as 0. And so you get negative 3 halves as your second horizontal asymptote.